Is everyone good with the warm-up, first of all? I thought that was an interesting set of questions there. Conjugate to, right, hold on. On the homework, what's the big takeaway there? All of them on the homework had a pre-image of the unit square. So let's jump to one of these here. Okay. So that's we might call the pre-image. And then the image, which is the result after having multiplied by, in this first case, 3 plus 4i, you get what? For all of these, you get another, well, actually they're all, I say this to some people in the back row, they should all still be squares, okay? Except they're what?
They're like diagonal.
Yeah, they're rotated and dilated, all of them, okay? So here's a little applet I constructed for our benefit to watch this happen.
How do you make one?
GeoGebra, man.
I didn't know what you were home.
Yeah, I mean, it's, yeah, yes. See, look, Mr. Chase Math right there. Thank you, thank you. It is my job, you know.
This is what you do at home in your free time. Like,
yes.
You could be hanging out with your kids or your wife, and you're like making applet.
Now, to be fair, my daughter, I made this apple the other day, and I made her slide the things around. She was sitting on my lap, and she enjoyed making adjustments. See, we're having a family time together with the applet, okay? It's not an either-or situation, is all I'm saying.
Wait,
Okay?
Mr. Chase, would you make this applet?
Yeah.
Yes. Oh, you use Java? Do you use Java?
No, I use GeoGebra. It's just yeah. It's all good. You can use GeoGebra and make your own applet too. It's pretty easy. So 3 plus 4i, if you multiply, is that what you got, friends? Okay. What was the next one?
It was just
-3 plus 4i.
-3. Are you watching? There we go. Is that what you got for the next one?
Yeah.
And then from that, should I do this one?
And then is it -3 minus 4i?
Yeah. Yes. Wait, it just screen
I know.
I did this wrong.
-3 minus 4i, yeah.
Hey.
Yeah, is that, you're checking answers here. And on the last one, 3 minus 4i? 3,
Yes.
yeah?
3 what?
3 minus 4i should look like that.
Yeah.
And then 2 plus I is the very last one.
Sure, 2 plus I.
I.
2 plus I is the last one.
Yeah.
2 plus I.
I don't know what the formula is.
And by the way, this cute little applet works if we adjust the thing that we're starting with to be something other than a square. The things we're saying here apply, of course, to anything in the plane. If you take like a smiley face and multiply it by 3 plus 4i, it dilates and rotates it, right? Anything you like, any set of points, this would be the action that is done to those points. It's just a unit square is very telling of what's happening, but you could do it with, this dark shape or something.
Mr. Chase, can you try a smiley face?
I don't think I can do it with. I don't think I can do a smiley face with these 4 points, but.
You can make just a smile. The one, not the eyes. I don't think my teacher.
I could modify this to do it, but I'd have to launch the Yoga, play around with it. So as you did this exploratory challenge here, it maybe isn't a huge surprise. Can someone describe why it's maybe not a huge surprise that this is happening? Why, when you multiply by a complex number, are you dilating and rotating? Explain in terms of things we learned on even the first day of complex numbers. Josh.
It kind of like shapes, like changes like the length of it. So the complex number, the I value is kind of like a rotation, and then so it rotates the shape around.
True. Yeah. If you're just multiplying by I, well, let's put a finer point on it here, right? By what is the dilation? What dictates the dilation? If you're doing like 3 plus 4i, what was the dilation factor? Why? Yeah. Yeah, and what is that? For the complex number, we've been calling that most recently. Yeah, magnitude or what? For polar one. Yeah, it's R, right? So it's how much did the dilation happen by when you multiply by a given complex number? Well, the R value, right? That's what the dilation will be. And what about the angle? We're thinking about how we multiply complex numbers in polar
Tangent
form.
negative 1 of e over.
It's just theta.
Yeah, it's like the theta for our complex number that we're multiplying by. So if we're doing 3 plus 4i,
Arctan
then you figure out what r is and theta is, and you'll have the dilation factor and the rotation angle. It's just a matter of thinking about these numbers, all of them, in polar form.
Thank you.
Okay. All right. Well, with that in mind, again, we're on a mission here to put a nice bow on all these different kinds of transformations. Right. We've been doing talk now about complex numbers and how those geometrically affect points in the plane. We've been talking about matrices in that light recently. We've been talking about vectors, and even you have a lens from geometry class on what it means to take R2 and make some transformation of the points in R2. Get this idea of the pre-image and the image. Anyway, so we wanted to try and wrap this up with a bow. Can we come up with today, the goal is, say you're multiplying by 3 plus 4i, can we come up with a matrix that does the same job as your particular complex number? You give me a complex number that does some dilating and rotating. Can you come up with a matrix that you would multiply by to do the same job? So that's going to be something this leads you through a little bit here. Yeah, next.
I'm not sure if this is right, but like, do you make like a if your coordinates are like up down, do you make like a matrix that's left right, and then make the left number the real part, and then the right part the complex number?
We'll see. We'll see. Maybe not quite as simple as that, but you're on the right track here. I mean, we want to think back to all the stuff we did with matrices. So go ahead and first verify this. Then fill in the blanks here. Notice now we're out of the realm of complex numbers by the time we're at number 2. And then fill in the matrix. Tell me what's going on. I'm going to be calling some people up here to fill in the blanks. But not be tied to these numbers.
Yeah, it's like not the slime. And a lot of Asian stuff.
But we are doing it in 3D.
Yeah. I mean, well, like, it's just
So we work on number 1. As you're working on number 3, think about the fact that what kind of matrices are we looking at here? There's just going to be empty brackets there. So the first matrix is a what by what matrix. 2 by 1. What's the second matrix? It's a what? The 2 by 2 matrix, right? So in those next 2 matrices that are blank, the first matrix is a 2 by 1, just a column matrix. The second matrix is, I mean, you can work this out just by like thinking about the math here. Of course, it needs to be a 2 by 2 matrix. You're going to multiply it by a 2 by 1 matrix. did a nice job on number 1 and 2, so you can glance up there and see what we're looking at. So far, so good. Michael. Go just copy that what's up there. Figure it out for yourself first.
Wait, they erased my name again.
So for the matrix, could you have an A, negative B, and a B, or does it specifically have to be BA on the bottom?
Yeah.
So why do you have to have BX plus AY? I was just wondering, instead of like AX plus BY. I mean AY plus BX.
You could, but then if you multiply it, I mean, we need it to be true that when you multiply this by, these have to correspond, right?
Oh, so does it matter? If on that matrix you have AY plus BX, can you change it to A, negative B, A, B, or can you not do that?
What?
Like, okay, like,
I mean, if you switch this, my only question is, if whatever matrix you have, when you multiply by xy, do you get this? And when you multiply this row by this column, do you get this?
AX minus BY.
If you do, then it's fine. You see that this one works?
I see if this one works, but like, if you switch the bottom, like, two things, would it still work?
I don't think so, because if you have these switched, if you have a A here and a B here, then you'd get AX plus BY. So that's not what we have.
Oh, I get it. I'm sorry.
So if someone comes to you with a square matrix and says, hey, my matrix, all it does is dilate and rotate. That's all it does. Then we know that that matrix has to have what form here? Well, this form. So in particular, if someone said, oh, I don't know, that my entry here is 5 and my entry here is 7, right away I know that's not a matrix that only dilates and rotates, right? Because then we say that it would come in the form where these two things are equal. If all it is a dilation and rotation, that these two things better be the same number, for example. Does that help, Arrow?
Yeah.
So what do you demand? What demands do we want to write down for A, B, C, and D? Like,
Well, A equals B.
good. I'll write it down for you.
C negative B.
Good. Right? Well, because we just established that if all we're doing is dilating and rotating, then this is the form of the matrix that we're using. someone brings me a matrix, I can tell right away whether it's simple dilation rotation matrix. If it is, then it'll have the form like this, right? These two numbers better be equal on the main diagonal. These two numbers better be the opposite on the off diagonal. Yeah.
But if you just had a 1, 0, 0, 1 matrix, wouldn't that still fulfill the requirement and neither rotate nor dilate?
Say it again. 1, 0, 0, 1.
Yeah.
Absolutely, that's a trivial rotation and dilation, right? So it fits in the category. In fact, the next question is in fact very close to what you're just now saying. Can you write down a matrix that only dilates? It falls under the same rule category, right? This is still only dilation is still in the family of things that only dilate or rotate. So what would it look like for you to find me a matrix that only dilates by a factor of r? Please use r now as the thing that we're dilating by, okay? So go ahead and write down what you think that matrix would be. Maybe I'll take a volunteer. Yeah. Absolutely. Yes. Good. Now let's use the language that's given in the problem. What letter? Yeah, Dina asking you a question. Is this still the same kind of matrix transformations we were doing before? Yes. Yeah, this is still, these are yes. That's the point. We're trying to make a connection between these things. So Dina said with a yawn, she's like, okay, so all you want me to do is write down this? What'd you say, Dina? And the answer is yes. That is in fact all we want you to write down. That fits with that fits with what we've just been saying, right? Try it on a point if you like, doesn't it? Just what does it do to x, y? It gives you the point instead. Rx, ry, doesn't it? You multiply this by a point x, y. Okay, so yeah, this is new, or maybe it's just old, actually. Okay, maybe we didn't learn anything just now. Okay, great. What about okay, this one's a little bit trickier now. This whole idea of rotation. This time I'd like you to write down a matrix that only rotates by theta, but does not dilate at all. So again, I'll take a volunteer if you think you can help us out there. Write it, and we'd like something all in terms of theta. Abe, you think you got it?
All four.
Yeah, all four of things in terms of theta, and we shouldn't have to refer to r at all, but go ahead. Well, what's A and B? I mean, maybe we should think about what A and what are A and B in our situation. Go back to think about polar form, all that, right? Like, if it doesn't dilate at all, then A plus BI. What's A? What's B? In terms of theta. What's A? Again, if you don't have dilation. If all we do is rotate the point, what is A and what is B in terms of theta? Huh? Well, I want something to be in terms of theta here.
Oh wait, never mind. This is exactly what. Wait, isn't it exactly? Oh, okay. It is. So
Yeah. I was hoping you'd pipe up, Katie.
Oh wait, no, I didn't. I misunderstood the question.
All right, so if you're multiplying by something that rotates by theta, then what must A, B, and B be? If R is 1, right, well then what must be A and B? Think of Euler's equation here. Think of polar form. Cosine theta and sine theta. Right? Okay, so I think we're ready to write this. But we're using the form we used earlier, right? A negative B, B, C, A, right? All right, so let's replace all those with just cosine theta and sine theta for A and B. Okay, so here we go. What do we, help me out. cosine theta, negative sine theta, sine theta, and positive cosine theta there. Okay. Now, one thing I'd like you to check, just to make sure this isn't a dilation, can someone check the determinant of this for me? Take the determinant of this matrix quickly. Go ahead. What do you get? What's the determinant? Regardless of what theta is, the determinant of this matrix is 1, which means it does what to the area when you multiply this by a vector? The area is the same. Now, that's not a tried and true test here, but I just want to make that observation that certainly any rotation should preserve the area. It shouldn't mess with that. This is not a dilation, or else the determinant would be something other than 1. Yeah. The determinant, what did I say? The determinant would be something other than 1 if it was a dilation, but it's not a dilation. This is simply a rotation. And now in the final analysis here on number 7, let's write, this is the big moment, let's write a matrix that represents doing both at once with r's and thetas in it. So we need 4 entries. What happens if you do both at once? Write down what you think that you would get there. Check with your neighbor.
Alright.
Here's one way. How are you thinking about this? I don't know, people out there. One way you could be thinking about this is, remember how we talked about matrix transformations? And how do you apply 2 at once? How about you just do one and the other by doing what with the matrices? Multiplying the matrices is, for matrix transformations, is composition, right? So how about you just multiply your answers from 5 and 6? Now you might be worried, well, which direction? Do I do 5 times 6 or 6 times 5? Doesn't matter, because dilations and rotations commute. Doesn't matter what order you do a dilation and a rotation in. I think that makes me think that it won't matter which order for this particular set of matrices, that it won't matter which order you multiply them in, and you'll get your answer for number 7. Anyone have it yet? It's basically the same answer as number 6, except you agree with Katie? So, yeah, we get what? Anyone? Well, hold on. Let's do it in terms of r's and thetas. All I want to hear about. I don't want to, right? All in terms of r's and thetas. Yeah, it should just be what we had on number 6, but just with, yeah, so r cosine theta, negative r sine theta, r sine theta, r cosine theta. Yes, sir. You get a high five for noticing the typo. Yes, you'll notice that at the very top of the worksheet I just passed to you that there is a typo at the very top. Please add, I fixed it up on my slide, but please add this R. The worksheet I just gave you, okay? So the result we just established, just within seconds ago, is at the top of this next worksheet. And now I'd like you to just kind of play with this idea. What if you want to get a matrix that dilates by this factor but doesn't rotate? What if you want a matrix that doesn't dilate but rotates by 45 degrees? Make it. What if you want a matrix that dilates by a factor of 7 and rotates by 30 degrees? Do it. Right? You got this. You got this. All right, and that's your homework.
So just this worksheet?
Yeah, just that worksheet.
All right.
Tomorrow is IB problems. Test is Tuesday. I'll give you the IB. I'll give you the review guide after the IB problem, unless you desperately want it now.
What's the IB problem?
IB problem is on stuff from this unit.
Oh,
Not this though, but
not this.
stuff that we've been doing.
Okay, thank you. Our IB problem?
Is it what?
No, we keep it.
Yeah, keep your quiz. Eventually I will, I'll have you put it back in your folder, but I want you to be able to look at it as you study and think about either both the reassessment as you head toward that, but also the test on Tuesday. Keep in mind your IA is also due on Monday.